The trisection of an angle is a classical topic in 2D geometry. It can't be solved by straight edge and compass alone, and that's why over the centuries many other constructions were found, including one by Archimedes, which I always thought was very artificial and a little bit contrived really. I'll explain that construction to you now, and I'll also explain how I think there might be more to it than meets the eye in the beginning. So let's start first with the construction itself. Here is an angle alpha and a red spiral, an Archimedean spiral named after Archimedes himself. And it has an equation, which is r equals theta, which expresses that this curve, this spiral, is like a circular motion, except that the radius depends on the angle theta, where you're at. So if theta is 0, then the radius is 0, so we start in the origin, and then we go round clockwise, anti-clockwise, and the radius becomes larger and larger as we go out. For example, let's see what happens at this point of intersection when our angle theta equals this prescribed angle alpha, which we want to trisect. So then the radius at that angle theta equals alpha, so the radius becomes alpha. So here the radius is exactly equal to this arc length, and that allows us to trisect the angle, like so. We first trisect this radius using straight edge and compass, and then so here we have like alpha over 3, 1/3 times the radius, and at this radius alpha over 3 we draw a circle, and if we intersect it with the red curve, what happens is that r equals alpha over 3 and therefore theta equals alpha over 3, so we have trisected our angle alpha. Now, why is this a bit artificial? This curve comes out of nowhere. We don't even know how to construct it. Plus, it seems contrived in such a way that an angle, theta, is forced to be equal to a line segment, r. So we can in fact straighten out this curve here, this circular arc, straighten it out into a line segment and then trisect it. So it seems rather magical. It seems rather contrived, but then again, it was thought of by Archimedes himself. So maybe there's more to it. But first, I need to address something. For example, why do we choose this point here? There might be other intersection points. In fact, let's zoom out a bit. If we zoom out a bit, we see that this curve goes on. So this is theta equals to 2 pi. So we made it one full circle. And then zooming out more, we see that in fact, this curve will intersect this side of the angle many times. Now, what would happen if we would do this construction with this point, for example? Where is it? Well, this point was theta equals alpha, then alpha plus 2 pi, alpha plus 4 pi, alpha plus 6 pi. If we were to do a construction with that one, trisect alpha plus 6 pi, what do we get? We get alpha over 3 plus 2 pi, which is here. If we intersect it with our curve, we get alpha over 3 plus 2 pi. That's the angle we get. So that's the same as the alpha over 3 what you got in the beginning. So that's all right. That's fine. But you see that we cannot take this point or this point. So we can take the first intersection of this spiral with our side, or the fourth, or the 7th, or the 10th, but not the 2nd or the 3rd. Now what happens if you do that? I'll leave it up to you. It all comes out in the end, of course. Okay, so that clears up that a little bit. But there's still the issue of this artificial curve, this artificial Archimedean spiral. But to see where it comes from, I have to take you into another dimension. So in fact, we've been looking at the top view of a three-dimensional picture. And that's a three-dimensional picture of a cone. Here, let me show you. Here comes the cone. Now, whether we trisect this horizontal line segment here or the slant line segment on the cone doesn't matter. It's a vertical projection after all. So if we can trisect that one, then the projection will trisect itself as well. However, this conical spiral here is also not very intuitive, at least not to me, but things get even more clear if I show you that this projection is in fact another projection of something much more natural. So what we do to see this is to project this cone outwards horizontally from its central line onto a onto a cylinder. Here, let me show you. So this is just a horizontal projection of whatever happens on the cone from the central line projected onto a cylinder. And now the spiral that we started with is much more natural. In fact, on the cylinder it becomes a helix, which is the equivalent of a straight line on the cylinder. In fact, if you were to cut open the cylinder and make it flat, then this red helix will in fact look like a series of parallel lines. Now we won't cut it open because that will straighten this circular arc, and then we can use straight edge and compass, but we won't do that. My point is that this red curve is now a geodesic. It's just the shortest distance from A to B. So it's completely the equivalent of a straight line on a flat surface. And if we were to remove it just temporarily, we see what we have done. So here was our blue line segment, and we trisected it into 3 equal parts. And then we have this nice big rectangle here. And if we just draw in the diagonal of that rectangle, which is another helix, so it's the short distance from this point to this one, so it's the equivalent of a straight line. It's another helix on the cylinder. And we can see that using similar triangles, so we have a right triangle here, another right triangle here, and a third one here. Since we trisected this vertical line segment, we have trisected this diagonal, and we've trisected this circular arc here. So that's basically why our construction works. But then we actually don't need the circles at all. So if we leave the helix here and we draw this diagonal which we had, we can see that instead of considering right triangles, we consider these triangles here. One of them, here's another, and here's the third. All of them again similar. And since we have here in a vertical distance the same trisection, type of trisection, we get a trisection of the diagonal again, and we get a trisection of these parts of the helix. So in fact, that's all we need. We only need a red helix and a green helix, which is the diagonal. So we look for the fourth intersection point of our red helix with this vertical straight line, and we connect the two with a line on the cylinder, and that's all we need for the trisection of the angle. Now, if you're wondering how to get these parallel lines, basically they're simpler on the cone. You just take the tip of the cone and you connect them by a straight line through these points. And so that's what you get on this 2D picture. So in fact, I argue that it's simpler not to consider one of these spirals, the original one, but also another one here, which does depend on the problem at hand. To show you that, I'll change the angle slightly. So as the angle changes, the red spiral doesn't change at all. It's just an arbitrary line on the cylinder surface. And the green one, which remember had to be a specific diagonal, it will change. In fact, the equation for the red spiral, we took it to be r equals theta. It can be r equals c times theta for any c. But the green curve has to match. And it has to have a proportionality factor to the first one, which is alpha plus 6 pi over alpha. To see why this works, for example, let's put in theta equals alpha. The red curve will be on this side of the angle, of course, which is down here. And substituting alpha equals theta, the numerator and denominator cancel, and we get alpha plus 6 times pi. Where is that? Well, this was alpha plus 2 pi, alpha plus 4 pi, and indeed alpha plus 6 pi. So the red and green curve indeed intersect in this point here at alpha. And of course they also intersect at alpha over 3. To see that, the red curve is simply at alpha over 3, which is down here. And substituting theta equals alpha over 3 gives the alphas cancel, and you have still 1/3. So we have alpha over 3 plus 6 pi over 3, which is alpha over 3 plus 2 pi. So alpha over 3 plus 2 pi, where was that? Well, remember our original construction where this was alpha plus 6 pi, and we trisected, and we got alpha over 3 plus 2 pi here, and we move it over onto this blue circle, and indeed we get an intersection of the red and the green curve. So I would argue that not only is the construction of Archimedes interesting, perhaps he thought of cones and cylinders as well, and I think it's in fact more natural not to use one of these Archimedean spirals, but another one. Which, it's difficult to construct in the 2D picture, but the construction on the cylinder is very, very natural. And you just project onto a cone and then project onto the on the flat surface here, and this is what you get. Now the construction on the cylinder I learned from this 1674 paper by the Italian mathematician Viviani. And he wrote, well, if it's allowed for Architas to use a cylinder and other 3D objects to construct the trisection of an angle, perhaps it's admitted for me to also use a cylinder and a helix as my basic tools. And in fact, I would argue that not one helix, but 2 helices, which are equivalent to 2 Archimedean spirals, is better than one. I'm not sure that Archimedes followed this line of thought. He surely didn't use these 2 spirals, but he might have, and I think it's a very elegant argument. So in fact, I think you could call this a trisection by using a straight edge only, but a very strange one. In fact, we use a normal straight edge to construct the angle, perhaps even a compass for that. Then a cylindrical straight edge to use to construct these red and green spirals. And then a conical straight edge to produce the lines that we see here. In any case, I hope you agree with me that this construction by Archimedes is worthwhile after all.